Lesson 6. Beam deflection. Last lesson we had both beam stresses. Now we ask how far the beam actually sags under load. On the exam you almost never integrate the elastic curve. You match the support and the load to a standard case and read off the maximum deflection. 3 one-line ideas. Deflection comes from a table. The deflection scales with the load over the flexural rigidity EI, and the span exponent and the coefficient are set by the support and the load type. Get those, and deflection problems are a lookup. Here's the problem. A simply supported steel beam spans 3 meters and carries a 20 kilonewton load right at midspan. The section is a solid rectangle, 50 wide by 100 deep. Find the maximum deflection at the center. Then we'll swap that point load for a uniform load and see exactly which piece of the formula moves. No integration. This is a table lookup from start to finish. Concept 1. Deflection is a table lookup. Every standard case has the same shape. A coefficient times the load times the span raised to a power, all divided by EI. That EI is the flexural rigidity, the material stiffness times the section's moment of inertia. A stiffer or fatter beam sags less, so EI always lives in the denominator. The handbook prints the maximum deflection for every common support and load pairing, so the whole task is picking the right row. Concept 2. The 3 cases you must know cold. A simply supported beam under a uniform load, a simply supported beam under a central point load, and a cantilever with a load at its free end. Notice the denominator is EI in all 3. What changes is the load, the coefficient out front, and the power on the span. Fix the support first, then the load type, then read the row, and note where each peak lands, mid-span for the simple beams, the free end for the cantilever. Concept 3. Read the exponent and the coefficient. Put the 2 simple beam cases side by side. The point load carries the span cubed with a 1/48 out front. The uniform load carries the span to the 4th with a 5/384. 2 things change: the coefficient and, more importantly, the span exponent. Cubed for a point load, 4th power for a distributed load. Grab the wrong exponent and you're off by a whole factor of the span, which is an order of magnitude miss. Setup. Build the table, the load, the span, the section, and steel's modulus up top. Then a blank with its formula for the moment of inertia and for the deflection. Then commit to 1 unit system, newtons and millimeters throughout, so the modulus is in megapascals and the deflection comes out directly in millimeters. The 2 lookups are the material modulus and the section's moment of inertia. The rest is given. Solve. Part 1. The central point load. First the section. Moment of inertia of a rectangle is BH cubed over 12. Then the matching case, PL cubed over 48 EI. Drop in the load, the span cubed, and the flexural rigidity, and the deflection at midspan comes out to 13.5 millimeters. Notice the span cubed term carries the numerator, which is precisely why every length has to be in the same unit. Solve. Part 2. Swap the point load for a uniform load on the very same beam. Now it's 5WL to the 4th over 384 EI. The support and the section are unchanged, only the load and its formula move, the coefficient, and crucially the span exponent, which climbs from cubed to 4th power. The deflection comes out to about 20.25 millimeters. And a caution, the loads here aren't equal, so this isn't a fair magnitude contest. The lesson is which term in the formula changed, not which load sags more. Final answers. Same section, same flexural rigidity, 2 loads. The central point load sags the beam 13.5 millimeters. The uniform load, 20.25. In each case, the support and the load picked the coefficient and the span power, and every length stayed in millimeters. Match the case, evaluate 1 formula, watch the units. That's the whole workflow. Traps. 3 ways deflection bites. 1. Match the formula to the support and the load. Simply supported versus cantilever, point versus distributed. Grabbing the wrong row is the number 1 miss, so read the boundary conditions first. 2. The span exponent is the 4th power for a distributed load, and the cube for a point load. Swap them, and you're off by a whole factor of the span. 3. Keep the EI units consistent. modulus in megapascals, inertia in millimeters to the fourth, span in millimeters, and the deflection lands in millimeters. Mix meters and millimeters, and the span term quietly falls apart. Quick recall. Every standard case is a coefficient times the load times the span to a power over EI. Simple beam under a uniform load, 5WL to the fourth over 384 EI. Simple beam under a central point load, PL cubed over 48 EI. Cantilever with an end load, PL cubed over 3 EI. Golden rule, fix the support, fix the load, read the row, fourth power for distributed, cube for point. Next up, Lesson 7, Principal Stresses and Moore's Circle. We can now check a beam for both strength and stiffness, bending stress, shear stress, and deflection from the standard cases. Next, we combine stresses at a single point, how normal and shear stresses rotate together, the principal stresses, and Moore's circle for reading them straight off. Everything's at pprepengine.com. Cheat sheet, worked solution, and a quiz attached here. If the course helps, subscribe.